Hello everyone, this is Dr. Ali, and in the previous session we solved this maze problem using recursion algorithm. But today we want to solve the same thing, same problem using the stacks or using the loops basically. So I want to keep this valid because I want to use this again, and I just comment out what we had last session. And to give you a brief that what is this stack function and how we want to solve it is that imagine if we are now in any location. Imagine we are here in this position, and now we basically capture all the possible next move in a queue or in a stack. So if I am here, the next moves are this one, this, right? Next possible moves are these three. And then I will store them in a stack. And then next time, if let's say imagine we move here, then I again append or move the next possible moves when I'm here to the stack, which is only this one. Remember, we cannot go back because we already visited here. And if I'm here, the next move is these are not available because these are black. Next move is here. And if I'm here, the next move is here and here, and so on and so forth. So at each cell, at each position that we are, we append the next possible move to the stack, and then we pop from a stack and we move from there. So let me show you in code, maybe it makes it more clear. So first we have like the queue or a stack. And then just one important note is when I'm using the stack, no longer we are calling the same function again, because that's for the recursion. But if you want to use it this stack version, we definitely need to have a loop, right? That's what I put a loop here. And remember, even the recursion is kind of is a loop, but it's internal loop. We are not defining a loop in the recursion because when in a recursion, a function calls itself. So that's why it has this concept of loop in it. If you're not familiar with it, there are some other videos that I recorded for that. You can check those. But anyway, so I'm here saying if the length of the queue is not zero, it means that if we still have next move, then keep doing this. If there is no, if this queue is empty, it means that there is no move. So we're done. There is nothing else we could do. Um, so of course at the beginning I call it is empty, but I will add something the first starting point into the queue. So at beginning it won't be empty. Anyway, so when we popped one next move from the queue, I extract those parameters that I already explained in the previous sessions. What are these? And then I check if that start move is equal to goal. It means that we reached already to the goal that we want. So I increase the number of solutions and then just print it. Print the solutions that we have with the number of moves that we reached from the start to the goal. And then exact same code that we had for recursion, this part. The only difference is in the recursion version, I was calling the same function instead of this part. But here I append the next move to the queue instead of just calling the function. I append and say, okay, if we are here and this move going to the right is valid, then do what? Append it in the queue, meaning that this is a valid move for the next time that you pop from the queue. This is a valid that's the valid move. So it means that you can start from there because that's a valid and be added to the queue. Same thing for the left, right, and up and down. So I just did that part. And then at the end, we just say how many solutions we have, right? So this is the queue total solution, which we updated it here. Whenever we hit the goal means that the solution was valid and we reached from the start to the goal. And we increased it that queue total solution just with one step. And now let's run it. And I didn't change the maze with our previous example we had in the recursion for just sake of comparing the result. So we start from 0, 0. We want to go 4 and 4. And this is the visited at the beginning, which all was false except this 0, 0, which is a starting point. And this guy also take care of the number of moves that we have. And this line, I just call this function that I already explained. So let's run this. And this is the solution we have. Let me copy this and put it just next to what we have, what we had next our previous session, to just compare the solution. So this is what we had from previous session using recursion. And now let me copy this guy here under it. So just compare for the sake of comparison. Both of them, it says total number of solutions are 5, but the order of solutions are different. So I mean, this guy for the recursion first give me go all the way right and go all the way down, but that solution is the last solution we have here, right? In our, we don't care this is the first solution or last solution, as long as it's comprehensive and it has all the solutions, we good. So if you check any other the solutions we have in recursion, you can find it here, definitely. For example, let's say this one. Where is this one with 16 move? So 16 move. This one. This and this are the same solution, right? So this is how it works. Just one question from you guys: that what will happen if in the recursion, or even if even in this stack development, if I change this, let's say I swap these two if statement, right? So I completely copy this, paste it under this. What will happen, right? Does this change the solution, or what will happen? What will happen at the outcome? Or imagine I swap these two as well, right? So the hint is the solution is still valid. Nothing gonna change except the order of the solutions. Same as here. If I imagine this, if I changed it, I copy this and put it all the way at the end, what would you expect to see? Please leave it down below in the comment section to see if you have any comment on this. And if it is still not clear and you need some more videos on this, please let me know, so I'll create some different way to explain this. That's it for today. Have a great day, everyone.